this video we show the high-speed digital design flow from Agilent that helps you cut through the challenges of today's multi-gigabit standards. Agilent EEsof's tools provide views into the time and frequency domains, revealing underlying issues and allowing you to anticipate and address problems, accelerate your design process, and achieve your design goals. This diagram illustrates the design flow. We'll walk through each section, starting with how a SerDes vendor uses Agilent's electronic system level tool, System View, to create an IBIS AMI model of a multi-gigabit I/O of an IC. System View allows the SerDes architect to create a system-level block diagram of the complex signal processing functions on the I/O of today's chips. Then quickly and easily create the algorithmic modeling interface, or AMI model, for use in the AMI flow that was added to the IBIS standard in version 5.0. System View reduces the time it takes to generate AMI code from months to hours. Now that we have models of the transmit and receive ICs, let's look at using the Advanced Design System, or ADS, for pre-layout design and analysis. Here's an ADS schematic ready for pre-layout simulation. Notice the IBIS AMI models of the SerDes transmitter and receiver generated using the process in the previous step. The schematic also includes a model of 4 coupled traces. The trace models in ADS allow you to model traces on multiple layers with variable width and spacing. This allows you to optimize these important parameters in pre-layout scenarios. Schematics can also include many other components such as vias, discontinuities, and as we'll see later, S parameters and fully integrated EM models. This schematic is set up to run the ADS channel simulator for fast linear simulation. We could also use the transient convolution simulator to verify channel performance with fully nonlinear transistor models. Both simulators make use of patented passivity correction and causality enforcement to ensure accuracy. ADS also has built-in design guides to help you quickly and easily set up simulations for standards including PCI Express, USB, DDR, and HDMI. Here are the results of the simulation, including waveforms, eye diagrams, bit error rate, and bathtub curves. ADS's powerful data display allows you to easily post-process the simulation results. After constraints have been determined and the layout is complete, critical nets can easily be brought into ADS through tight integration with enterprise layout tools. First, identify and export the nets. Then, bring the nets along with all the vias and the imperfect power and ground planes into ADS for post-layout analysis. Now EM simulations can be performed on this critical portion of the layout structure using Momentum, the integrated 3D planar EM solver. The 3D view of our imported layout showing the current distribution from the Momentum simulation is useful in identifying problem areas. Momentum also calculates the S parameters for the structure and creates a model for post-layout simulation. Simulation in both the time and frequency domain helps you solve problems that would be difficult, if not impossible, to do with a time domain only simulator. In this layout of a power delivery network, or PDN, the current distribution is once again used to identify problem areas. A model can also be created and used to compute the impedance of the PDN and help to determine decoupling capacitor values. For 3D geometries that are not planar, such as this SATA connector, EM Pro can be used to run either finite difference time domain or finite element method to analyze the structure. EM Pro interfaces with ADS to create models for channel simulation. 3D components can be integrated with an ADS layout to simulate overall channel performance. Now let's pull it all together in a post-layout analysis of the channel. This is an ADS schematic ready for post-layout simulation. Notice that now, in addition to built-in trace models, the schematic includes S parameter models that can come from simulation or measurement, and EM models of the critical nets. The results verify that we still have a reasonable eye opening even with the imperfections introduced by the actual layout. Finally, it's always important to validate simulation results with measured data. Here's a comparison of measured and simulated eye diagrams for a 16-inch backplane plus daughter cards. Notice how closely the measured and simulated curves match in the overlaid plot. In this video, we have shown the high-speed digital design flow from Agilent EEsof. Agilent provides the integrated time and frequency domain simulation tools that help you cut through the challenges of multi-gigabit digital design. For more information, please visit us at this website.